Group 7, this group of elements is called the halogens. Halogen means salt maker. If you see gen on the end, generation, if you like, generate is to make. So the halogens make salt. The halogens are group 7. Let me show you here. I've made a mess of this periodic table by now, but that's okay. We're looking at these, and again, there are only 3 that we can really investigate in the lab. These 3 here. Fluorine is fluorine is so highly reactive and very, very poisonous. You are unlikely to ever encounter fluorine. But chlorine, bromine, iodine, yes you would. Astatine, very rare. We don't need to worry about astatine. But let's have a look. We've got fluorine, chlorine, bromine, iodine. Fluorine, atomic number 9. Chlorine, 17. Bromine, 35. And iodine, 53. Now, we don't need to draw the structure of all of these, but what I will do is draw the first 2. Fluorine, atomic number 9, that means it has 2 and then 7. Chlorine, number 17, similar structure, but 1 extra shell. 2, 8, 7. I always leave my gap, if you like, the missing electron on the right. You can choose to draw it however you want. But I think you can see that these halogens, the group 7 elements, react by trying to accept an electron. An electron comes in from somewhere else to complete this shell, to make it stable. So now let's think a little bit, which one is going to attract electrons better? Maybe I just draw a couple of these. Okay, all I'm going to draw is the outer shell. So for fluorine, chlorine, I'm just drawing the outer shell, the so-called valence shell. These are valence electrons. So we're looking for an electron to come in and fill that space there. Now the attraction between these 2 is quite strong because they're pretty close together. There's positive charge in there and there's negative charge there. Opposites attract. If you have an opposite pair of charges close together, they'll attract more than, let's say, here or here. Can you see that? This distance is a little bit bigger. This distance is even bigger. So this is most reactive because it's small and the attraction to the nucleus is very strong. This is fluorine, this is chlorine, this is bromine. We'd have iodine down here. So the trend in reactivity decreases as you go down the group. Again, the trend in density increases always as you go down a group. These are bigger, more massive atoms as you go down the group. So let me just check the syllabus. Describe the halogens chlorine, bromine, and iodine in group 7 as a collection. Okay, blah blah blah. Let's take a fluorine atom. I'm just going to draw the outer shell. This is very unreactive. If fluorine is produced in a reaction, or chlorine, or bromine, or iodine, or anything like that, let's see another atom of fluorine. These are so unreactive that they will tend to pair up like this and make a covalent bond between them. You can see there they're sharing a pair of electrons. This is called a covalent bond, where a pair of electrons is shared. And we'd write this as an F2 molecule. We say that fluorine is a diatomic element. It's an element. Diatomic, di means two atoms. Two atoms make up a molecule of fluorine. Same with chlorine. So fluorine, chlorine, bromine, iodine. They all go around naturally occurring like this. Molecules joined up in pairs. Diatomic molecules. And one more observation here is their color. We've seen their reactivity. Fluorine is very reactive, chlorine is quite reactive, then bromine, then iodine. Fluorine, bromine, iodine. We don't need to talk about astatine. In fact, we will take fluorine off because the syllabus is asking us just to focus on those three. Chlorine is a pale green gas at room temperature. Bromine is an orange liquid. Bromine, by the way, is one of only two liquid elements at room temperature. The other one is mercury. All the others are solids or gases. Only two liquids, bromine. And then iodine is a kind of a grayish black solid. Look at that trend from gas to liquid to solid as you go down. That's further evidence that the trend is from low density to high density. Look at the trend in color. A pale color, a darker color, and the darkest color you could imagine. You could use this trend to predict what fluorine looks like and to predict what astatine looks like. This is the beauty of the periodic table. It allows you to make predictions about elements that you've never seen. If chlorine is a pale green gas, I would bet that fluorine is a gas. As we go down, if iodine is already a solid, I would predict also that astatine must be a solid. Now, if this is a gray-black solid, well, how much darker could you get than gray-black? Not much. Black, I reckon. Black solid. This, well, what's a paler color than green? Maybe yellow. I reckon yellow gas, black solid. So this is a use of the periodic table. It allows you to make predictions about elements you've never seen. There we go.